All right, so this video is dealing with the second part of 4.2, or what I'm referring to as 4.2.2. And the first thing we talk about here is compound interest. So compounding, when we compound, it means that in a savings account, for example, we stop, we calculate the interest that has occurred, and then we add that interest back to the principal. And so when we compound, that means the principal is getting increased by the amount of the interest that's occurred since the last time we compounded. So in this first example, we're going to compound annually, which means at the end of the year, we'll figure out how much interest you've gained, and then we add that to the principal. And now for the next year, the principal is a little bit bigger because you've got the interest from the previous year. Okay, so let's assume that P is going to represent the principal, the amount of money we originally put into the account. The interest is going to be R. So the interest, the account compounds annually, and that it pays interest R. Now, when you put interest into, it's a percent, right? Interest, the annual interest rate. When we put it into formulas, it's always got to be a decimal. So be careful with that. All right, so let's say that we put P amount in. So at the end of 1 year, we put the P in at the beginning of the year, and at the end of 1 year, after 1 year, we have the principal. Plus we have, let me cover up the rest of that so we can concentrate on just this one. We have the original principal, plus we have the principal times the interest rate. Okay, so that, let me see if I have my light on. Okay, let me turn the light on here. So then it's the principal plus the principal times the interest rate. Okay, and so we could factor a P out of both of those, and we get P times 1 plus R. Okay, so now that's now the principal. At the end of the first year, this is how much money we have in the account. And so for the second year, that now becomes the principal. So we had the principal before here. Now this is the principal for the second year's worth of the money being in the account. And then that principal gets multiplied by the R. And so you can see we could factor out P times the quantity of 1 plus R out of both of these terms, and that would leave us with 1 plus R. After we factor that stuff out, we have 1 plus and then R. So we could take those two 1 plus R's and write it as 1 plus R quantity squared. All right, so this is the amount of money that I have after 2 years at the end of the second year. So for the third year, that's now the principal. And so you could see in the third year, at the end of the third year, we have the original principal that started the third year. So that's our principal, plus the principal times R. And so you can see this kind of pattern continues. And so you can see that pretty easily, we could see that this formula develops that it's P times the quantity 1 plus R raised to the T, where T is the years. Notice at the end of the third year, we have it cubed. At the end of the second year, we have it squared. We didn't really write it, but it's almost like we could think of it as having a 1 at the end of the first year. And so this is the formula if we're compounding annually. Remember, compounding means that at the end of the year, they calculate the interest. That would be, this part here, and we add it to the original principal. All right, so what if we're compounding more frequently? So often bank accounts will compound once a month. At the end of the month, you get a statement, and they say, okay, this is the interest you've gained this month, and they add it to your account so that the next month, your principal is a little bigger. All right, so what if we compound more frequently than once a year? So the formula is a little more complicated, but not much. So in this formula, we have N. N is the number of compounding periods per year. So if we compound monthly, then N would equal 12, because we would do it at the end of each month, 12 months in a year. All right, so it's very similar to what we had before, but now again, each time I compound, I'm not going to add R. I'm not going to add the interest rate, which is annual. I'm going to add, say, 1/12 of that, right? So I don't get a full interest, times, plus 1. I don't add the interest for the whole year. I add 1/12 of that, okay? And then N also goes next to the T. All right, so let's use this formula in an example. So if $3,500 is deposited into an account which compounds quarterly, paying 3.5% interest, how much will be in the account after 8 years? All right, so pause the video, calculate that. It doesn't say what to round to. You can round to the nearest dollar, maybe the nearest penny, whatever you want to do. Okay, so the amount is equal to 3,500 times 1 plus, and then the interest rate. Now be careful. You got to put that in as 0.035. If you put it in as 3.5, then you're really calculating an interest rate of 350%, which means you would more than triple your money every year, which is really unheard of. And then quarterly, so that means this is a 4. And then 4 times t, and t for us is 8 years. Doesn't have to be whole number of years, but know that it has to be in years. Okay. So really, you just take a calculator and you plug all that in, assuming you do it correctly. Careful, you have to essentially raise it to the 32 power here. Don't raise it to 4 and then do times 8, because that might raise it to the 4th power, get the result, and multiply by 8. So got to be careful. You got to make sure that, depending on what calculator you're using, that it's actually raising it to the 32nd power. All right, and to the nearest penny, I got $4,625.32. All right, is what I got. And so if you didn't get that in your calculator, first of all, make sure that you used the correct decimal for your interest rate, but also be concerned with your order of operations here. Okay. All right, next one. Number 5. Bob wants to give his newly born niece $10,000 on her 18th birthday to help pay for college. Assume that he finds a long-term investment that pays 4.25%. How much money does Bob need to invest so that in 18 years he'll have $10,000? All right, so pause this video, figure this one out, and then resume the video. All right, this time we know what the A is. We want 10,000 at the end. So 10,000 is equal to, and this time we don't know the principal. All right, 1 plus, now be careful the interest rate. It seems like if I said 4, everyone would have no problem, but when I put a 4.25, that throws people off. 0.0425, right? Over, let's see, how much is it compounding? Assume long-term investment. Doesn't say how much we're compounding, so I guess we're going to assume that it's once a year. All right. So I didn't really need to put the 1 underneath, but I already had my fraction bar there, so I just put 1. So you don't really need that. All right, and then, so really, we want P is equal to 10,000, and then divide it by this stuff, 1.0425, because we could add those up, raised to the 8th power. So again, that's kind of just calculator work. Oh, not 18th power. So you can, put all that into your calculator. And again, you should get something like $4,727.49. Again, rounded to the nearest penny. If you were rounding that to the nearest dollar, it would just be $4,000 $4,727. Remember too, when we're rounding, we don't use the 9 to turn the 4 into a 5, and then use the 5 to turn the 7. So, if we're rounding to the nearest dollar, the 7 may stay the same, or it may go up, and the 4 is not big enough. So it would just be 4,727 if you had rounded it to the nearest dollar. Okay. Now, a lot of banks do not use compounding in different periods. Like, it doesn't compound monthly or annually or quarterly. Instead, they compound continuously. So this example is going to sort of demonstrate how we might arrive at that formula. So let's look at a rather simple example. So we're making it really simple. The principal is just $1. And to make it even simpler to calculate, we're using an interest rate of 100%. So that means you would double your money every year, right? 100% interest. All right, so let's just keep the numbers really simple. If we compound annually, so that means once a year, then n would be 1 in our formula. And so we would have 1 plus 1 raised to the, if n is 1, 1 times 1. So it would just be 2. So this graph sort of demonstrates not time, not like years here, but this is the number of compounding periods per year. All right, so if we compound once at the end of the year, then you would have $2. If we were to make this a 2, and then that would be a 2, so now we're here, then you would see you've got a little bit more. Now, normally the difference between compounding once a year and every 6 months is not that great, but here our interest rate is huge, right? 100%. So of course it's going to exaggerate that. But what's interesting about this is as I let the number of compoundings increase, and really I let that go to infinity, right? The number of compoundings per year is infinitely large, then the amount I have gets closer and closer to this asymptote. And that asymptote, you might say, well, where is that asymptote? It's somewhere between 2 and 3, and it's actually Euler's number that you might remember from science class. It shows up a lot in exponential functions in science class, sometimes referred to as a transcendental number. Euler is a famous mathematician, and it's just named after him. So it's 2.71828, and it keeps going, but that's essentially what it is. But that's not an exact; it just kind of keeps going number. So if we let n go to infinity, that's the same thing as saying we're compounding continuously, and so that formula ends up converting to this. All right, so E being Euler's number, and so that's what this approaches as we just get closer and closer. All right, so P again being the principal, E is Euler's number that we talked about right here, R is the interest rate, and the exponent is R times T now. T being time in years, and R being the interest rate, of course, as a decimal. So compounding continuously, it's like almost like a little magical elf is sitting there with an adding machine, and every millisecond, is just instantaneously, constantly calculating what little bit of interest you have and is adding to it, is adding to your account. So adding that little bit. Now, it's weird in this case, we saw such a big difference because the interest rate is 100% in this example. In real life, interest rates, you're lucky if you can get a 2% interest rate on a savings account. Maybe a 0.5% would be more likely, but sometimes with the higher interest rates these days, you can get a little bit higher interest rate. But with such a small interest rate compared to 102% or even 4%, you're not going to see a huge difference between compounding, say, monthly and compounding continuously. Now, if you do this for decades, yeah, you're going to see a difference. Or if you have really high interest, then yes, you're going to see a big difference. But generally, you're not going to see a huge difference between these. All right. So let's go to page 3 and do some examples of this compounding stuff. So suppose that $3,500 is deposited into an account which compounds continuously at a rate of 3.75%. How much will the account will be in the account after 10 years? So here you just have to make sure you're understanding how it's being compounded. Here it's continuously, and so now know that we will use the A equals P times E raised to the RT. Sometimes students, to help memorize this, calls this PERT, if that helps you memorize it. Okay, so how much is left in the account after 10 years? So we have the original principal, E, and then we raise it to the 0.0375 times 10. Now this one's easy enough. You might just move the decimal place once, right? So that you don't have to worry about doing this in your calculator. Now, how do we get E in our calculator? Okay, let's see if I have my calculator here. So, this is a graphing calculator. It's different than your calculator. I'm trying to see if I have another calculator around here somewhere. Yeah, I do. So these are the types of calculators that we use typically in class. So let me get this one out. So the E that you would have on this is it's an LN button. So if you look for an LN, we'll learn later on what LN stands for. But it's the second function of the LN button is E to the X. And so in order to do this in your calculators, let's try to get rid of the glare here. We're going to first turn on our calculators. Okay. So again, my calculator's got a little bit of a glare. Let's see if I can do this clear. All right, so now I'm going to hit my second button and then the LN button. So second LN, and notice it's saying E raised to the. So this is nice. It starts your parentheses. So now I could, in this example, type 0.0375 times 10, sometimes 10, all right? So now I know this whole thing is being used as the exponent, and I'm not accidentally going to raise e to this power, take that result, and multiply it by 10. All right, and so now I get that. Oh, I forgot to multiply my 3,500. So let's start over. So 3,500 starting, and then I can hit second natural log. So it's 3,500 times e raised to the 0.0375 times 10. So I did it all at once, so I don't have to worry about, All right, so that ends up giving me $5,092. Again, it doesn't say what to round to. In this case, point, I guess, 47. Let's do it to the nearest penny. All right, so 5,000. Let's put a $sign in front of that. $5,092 and 47 cents. Okay. Try the next one now. Suppose that you deposit $100 into an account which compounds continuously at a rate of 4.5%. About how long would it take the account to be valued at $5,000? All right, so set up that one. Let's just set it up and then we'll talk about it. So pause this video, write the equation, think about what it is we're looking for on this one. All right, so we set this up. We know what the final amount is, right? We want $500 at the end. We start it with $100. R is 0.045. Now the problem is we don't know what the t is. And the variable is up in the exponent. And so this one we can't actually solve at this point because we don't know how to get a variable out of the exponent. It was like what we were talking about on top of page 2. Remember, we couldn't do example 3, part C, because we had a variable in the exponent. We don't know how to get those variables out. The only way we know how is if we can make these bases the same. and we can't really make these bases the same, right? E and 500. Well, first thing I'm going to do is divide. I would divide by 100, so it would be 5 equals e to the 0.045t, but I can't get t out of the exponent. Don't know how to do that, okay? Can't make these bases the same, so we're stuck. So if we were going to try to estimate this, at this point we could do a little iterative process. What if t is equal to 5? What if t was equal to 15, right? We could calculate a. That's pretty straightforward. We just plug not into this formula, but we would plug it into this formula and see if we got something close to 500. So because this one we've already divided, right? So, or we could plug it into this one and see how close we got to 5. But after 5 years, we have $125. After 15 years, we have $196. All right, still really far away from our 500. So let's jump and let's say, well, what about if t is through 30 years? All right, that gives us. I did these calculations, so if you want to stop and do them yourselves, that's fine. $385. All right, so that's still not even close. Let's do 35. 35 gives us $483.07, and then finally t equals 36. So that would give us $505.31. So somewhere between 35 and 36 years, we would end up hitting this probably a little bit closer, maybe to the end of the 35th year. So closer to 36, but still, that's not, it's certainly a valid method, but we want more of a precise, exactly how much time. Not somewhere between 35 and 36 years is good for now, but we want, we're going to be able to solve this equation in later sections, after later sections, when we start using logarithms. Okay. So we're going to use a similar formula for other exponential models as well. A situation involving growth and decay. So growth and decay, you might think population growth. You might think decay as in half-life in chemistry. There's elements have a certain half-life. So y is the amount at a certain time t. Y sub 0, that will mean the initial amount. K is kind of like an interest rate, but we're not talking about money here. So it's a constant specific to the particular problem and the units in the problem. And so often we'll have to be either given K or we'll find K. Now this is slightly different than the formula that you sometimes use in science class. That uses something like y equals b 1/2, 1/2 t, I think, and where t is the actual half-life. I'm not sure that's the right formula. I have to stop and think about that for a minute. But you have one that's slightly different sometimes in biology and chemistry class. All right, so example 8. Assume that the population in millions of a country follows the following model. Okay, so this is the population in millions. The output would be the population. X, the variable here, is the number of years since 2000. So if it's 0, it's 2000. So what is the population of the country at in the year 2000? So that would be an x of 0, right? So we're essentially asking you to figure out what's f of 0. So pause this video and calculate that. So this is the, so if I put the 0 in here, this is all e raised to the 0 power. So that's just going to be, that part is just going to be 1. So it's 4.25. But remember, that's in millions, so it's 250,000. Right? So that is at year 2000. that's what this is, right? That's the starting point when time is 0. And so we really didn't have to, if we understood this formula, we wouldn't have really had to even try to do this. We would have just known, oh, this is the initial amount, right? Okay, according to this model, what will predict, I don't know, that doesn't sound right. According to this model, what is the predicted population of this country in 2025 and then also in 2050, assuming this model continues to that point? So what is f of 25? And then also what is f of 40? All right, so pause the video and calculate those. Again, that's pretty much just straight calculator work, but go ahead and calculate those. All right, so that's 4.25 e to the 0.0152, and then we're using, of course, 2025, so x is 25. All right, and plug that into your calculator. You should get 6,214,710. And then in the year 2040, x will be, of course, 40. And so now we have 4.25 e raised to the 0.0152 times 40. So plug that again into your calculator. So the population should be about 7,806,205. Okay? So, and again, they would have to give us the K in future sections. We'll revisit some of these formulas and practice them some more, and do more complicated problems once we start talking about logarithms. Again, we can't solve for K yet. We can't solve for T yet. So they have to give us both of those. Again, we wouldn't be able to solve for any variable in the exponent because we just don't know how to do that yet. We'll learn that, how to do that once we hit some logarithms, which will be the next section. All right, and so we'll revisit all these interest and growth and decay problems, and we'll go into a little more depth with them. But at this point, it's really just kind of straightforward stuff because we have to keep it simple. We don't know how to use our logarithms yet. All right, and so here is the homework due next class.